So, Mr. Fahad,
Hello, everyone.
hello. What is this? What is this tutorial? It's going to concentrate on 1.4 and 1.5, right?
I'm sorry.
This tutorial, is it going to concentrate on 1.4 and 1.5?
Yes. So in this tutorial, we will be covering 1.5 and 1.6. So 1.4 is not covered in the previous tutorial, and it will not be covered in this tutorial. So if any of you guys have any questions from 1.4, they can email me, or they can ask me if they have any. And if they want to watch a tutorial, so the other tutorial, it also covers the exercise 1.4. So if you want, then you can basically just watch that tutorial. By the way, can all of you guys hear me clearly?
Yeah.
And I don't usually read the messages when I am like having a video conference. So the best way is just to like say it instead of texting me, because I don't usually read the messages.
Okay.
Okay, so looks like there are not many people here today, only 9 of us. So as I mentioned earlier, like in this tutorial, we will be covering exercise 1.5 and 1.6. Okay, so maybe let's get started. Okay, I'm gonna share my screen now. Okay. Okay, let me know if you guys are able to see my screen.
Yes.
Okay. Okay, so this is your exercise 1.5. The book number page is 68. And we will start with the first question. And so we will not be going into the nitty gritty details of all the questions. So we will be just try to cover as much different ideas and scenarios as possible. And if you guys have any questions, just let me know at that time. Okay. Okay, so let's start. So for this question number one, so what we have to do is we have to translate them in these English statements. So here, this A, the reverse A here, it basically the upside down A, it's basically mean for all, and then this E, the reverse E, means there exists, and then there are of course different ways of saying it. Okay. So if taking the part A, so if I have to convert this into an English statement, so I will say for every real number x, there exists a real number y such that x is less than y. Okay. Taking part number B. So B is a little trickier, but the logic is basically just the same. So we'll say for every real number x and real number y, if x and y are both non-negative, then their product is non-negative, because we have this implication sign here. So if this thing happens, then this thing happens. Moving on to part C. So here we have three variables, x, y, and z. So we have to include them in our statements. So for every real number x and real number y, there exists a real number z such that x, y equals to z. Any questions?
Why just not saying positive instead of non-negative? Or
I'm
is
sorry?
it? Why just not saying positive instead of non-negative? Or
Over here?
yes, did we have to do it like this, or?
No, this is basically, I'm interpreting it as it is. So here we have x is greater than 0. So if we say positive, right?
Mm-hmm.
So you can also like, what do you have in your mind? Like, what do you want? How do you want to say?
Like if x and y are both positive, then the product is positive.
If x and y are both positive, right?
Yes.
Okay, yeah. So this would be the other way. Or you can also say it if x and y are both non-negative.
Okay.
Okay.
All right. Thanks.
Okay. If no more questions, let's move on to part number question 3. So question number 3, we have here we have this statement: x has sent an email message to y. So x represent n. This statement over here, q, x, y, it basically means x has sent an email message to y. And then the domains of both x and y are the students in the class. So we have to express this statement in English statement. Okay, so let's check on part number 1. So this will be, there is some student in your class who has sent a message to some student in your class. Okay, so because both of these are there exist, so there is someone who has sent some message. Okay, let's take part number C. So part number C is every student in your class has sent a message to at least one student in your class. Okay, because there exists. Okay, so we have to ensure that there exists someone. We cannot say, for example, that has sent a message to student in your class. Okay, we have to stress on like there is at least one student. Let's move on to part E. So we have every student in your class has been sent a message from at least one student in your class. Now here we have seen that just by reversing the order, so before here was X and here was Y, but now just by reversing the order, the statement actually reverses as well. So this is interpreted as every student in your class has been sent a message from at least one student in your class. Okay. Any questions?
I didn't quite understand the difference between the last two sentences.
Sorry, say that again.
I didn't quite understand the difference between the last two sentences.
The last two sentences?
Yes.
Okay, here basically, here, if you will see that the statement here, it means QXY be the statement X and sent an email message to Y, right? So it represents X where the domain for both X and Y consists of all students in your class, right? So here X, so this X here has sent message to Y, and then both X and Y are some student in the class, right? So here we have this statement that represents this: every student in your class has sent a message to at least one student in the class. But now because those variables are coming in a different order now, so X is coming later now and Y is coming before. So now because we have reversed the order, so we will also reverse the meaning of it. So before X has sent an email message to Y, so we will say that has been sent a message from at least one student in your class.
Okay, I understand now.
Okay.
Miss, I didn't get the example.
Same question.
Yeah.
Basically, we just reverse. It's not something like really big. We just reverse the order. So here we have this X who sent an email message to Y, which is represented by the statement C, right? So X has sent a message to Y, or here X sends a message to Y. But now because we have switched their order, so we will also switch this statement, how it's gonna be interpreted in English. So we can say that this here, every student in your class has been sent a message from at least one student in your class. Okay. So therefore, one takeaway from this is like the order matters. Any other questions?
Quick question. Don't we need to specify X and Y when we're expressing the quantifier in English?
We don't have to, because here we have specified the domain, right? It says the domain of both X and Y consists of all students in your class. So indirectly, they are basically representing X and Y. So when I say in your class, student in your class, it's the domain of X and Y.
Okay. Okay, thank you.
Okay, let's move on to the next question. So it's more or less the same question. So we have the statement here. WXI means that student X has visited website Y. And then the domain of X consists of all students in your school, and the domain of Y consists of all websites. Now, if we have to interpret this first statement in English, so it will be that Sarah Smith has visited www.att.com. Okay. Now let's do part number C. So part number C will be interpreted as likewise. So Jose Arias has visited at least one website. Okay, because of there exist Y, and Y, the domain of Y is here consists of all websites. Okay. Part E. This E is a little more trickier, but we will be using the same logic. So there is a person besides David Belcher who has visited all the websites that David Belcher has visited. Okay, because here we are saying that there is a person, so there is a person which is expressed by X, right? So there is a person who is not this guy and who has visited all the websites that David Belcher has visited.
Why did you use there is a person and not there's a student?
Well, you can also say there is a student. Well, student is also a person, right? So
I mean, in this context, like the domain is about students, right?
yeah, so yes, you're right. We should have restricted ourselves to the domain. So this is so this is an ideal practice to restrict yourself to the domain, but again, it's not about the grammar. As long as it is interpreted correctly, you will have the marks.
Oh, okay, thank you.
Miss, what about the WYZ after the implication sign for 5E?
Yeah, so basically here it means that, so we only have two variables, right? If you will see in the question, X,
Oh.
Y. But in here we have a third variable, that's Z. And that comes in play when there is an implication. So if this thing happens, then this thing happens. So there is a student besides David Belcher who has visited all the websites that David Belcher has visited. So this Y is, so this here, it represents like that there is a person.
You didn't include the Z because it's not part of the variables, right?
I didn't include it where.
You didn't include the Z in. You didn't include for your solution because it's not part of the variable. right?
Because this Z is in the question, right? But we don't know the domain of this Z, right? Because it's not in here, right? We don't know what does Z encompasses. So therefore, I was referring to it as a person instead rather than a student. But because a student is narrowed down to a person as well, so yeah, we can do that.
Why? I mean, the domain for Y consists of other websites, right?
Yes.
But when we look at the first portion of the statement, like when we have Y different than David Belcher, how would you interpret it in English?
When we have Y different than,
David Belcher.
so we don't have this name over here.
Like, how would we interpret it in English?
We just did, right? Here. What's your question exactly?
I just got a bit confused between the Y and the Z. That's the thing.
So here, Y basically it means that it's consists of all the websites. So Y basically represent a website. So we added this symbol, there exists a website, right? So whenever we use Y now, we are restricting ourselves like there exists a website, right? There exists a website. And then we are saying this David Belcher. Now, if you will look into this statement, right? So we have this Z over here. We're saying that this person is basically David Belcher, right? So we are basically saying that there is a person who is not this guy, right?
Oh, okay.
But he has visited all the websites that this guy has visited.
Okay, I understand. Thank you.
I don't get that who has visited all the websites that David Belcher has visited. I don't get that part.
So this implication over here, right? So before this, so if just look at this part. So if that there exists, so we are using these qualifiers over here, right? So which restrict our domains, like there is one person or there are many persons or there are all persons, or that restricts the domain, right? And then this statement in the brackets is basically creating the logic here. So we are saying that, so just forget about there is a student or all the websites. Just if we see here, so Y is not David Belcher. So here Y, so we know that this is not David Belcher. And what else we know? We know that David Belcher has visited this website, some website Z. We don't know which website is. So Z basically represents one of the website in that list of domains, right? In that list of domains of Y. Okay, so there is a website that David Belcher has visited, and that person here, it's not David Belcher, right? We have this and here.
So that's, oh, then the WYZ. What's that?
And then,
What's that from?
sorry,
Or I get that. Oh, okay. I think I get it now.
here Z, it means that
It's the website, right?
so Y is consist of, let's say it's a some set of website. Let me just pull up okay, here we have this Y and Z. So Y is a set of websites, right? Have you guys read the concept of sets? Do you guys know what the sets are? So let's say these are, so I can list down all the websites that are in the set Y, right? So there are so many of them that are in the set Y. But here, Z is a smaller set of Y, which contains the website that are both in Z and Y, right? So Z is a smaller set of Y, okay?
So is Z like a subset of Y?
Yes, so Z is a subset of Y. Okay, so Z, basically Y has everything that Z has, okay? So here we are saying that here, so David Belcher, he has visited, right, the site Z, and then we are saying here for all the websites, right, that are visited by David Belcher is visited by another person who is not David Belcher. This here, it means that that person is not David Belcher. This means that the list of websites visited by David Belcher. This here means that that person has also visited that same websites. Maybe we will do one or two more questions
I
and
get it now. I get it now.
maybe this one was actually a really long one. And maybe after you guys practice some few more questions, you will probably get it even better. Okay, let's move on to another question. So question number 9 here. So here we have this statement in English, and then we have to interpret those in what is it called? It's in the, let me actually maybe make it short. Okay, perfect. So here we have this statement, X loves Y, where the domain of both X and Y consists of all people in the world. Use quantifiers to express each of these statements. So for part number A, so we have everybody loves Jerry. Okay, so we say X for all X because it's everybody. For all X, L, we use the function L. X loves Y, but Y, we know that it's Jerry itself, so we will use Jerry. Okay, so everybody loves Jerry. So if it is everybody loves everyone, then we will say we will put Y here, and then we will put for all Y over at the front. Okay, so let's take part number C. So there is somebody, so there exists somebody, let's call it Y, whom everybody loves. So whom everybody, so let's say everybody, there's everybody. Then we use the sign, the function L, and then we put here X and Y. Okay, because we're saying there exists someone who loves everybody. Part E.
Miss, why didn't you use X for the existential part? Why did you
Why
use
didn't I use existential for the
what?
X?
Yeah, why didn't I use? Yeah, why didn't you use X?
Because here it says everybody, right? Everybody is it includes everyone, right? It doesn't include like only one person, 2%. It includes everyone.
Oh,
Okay, whom everybody loves. So that's what.
okay.
Actually, I understood till till the inverted AX, but why did you write like L of XY over there? Can you explain that part?
Here, if we look at the question, it says that XL of XY represents the statement X loves Y, right? It's a function. We have
Yeah.
to use the function. If we don't put
Yeah.
this L, we don't know what it represents. With this function, we know that it represents love.
Okay. Thank you.
Okay, so if I, let's say, put P instead of XY, the meaning will completely change and it will be uninterpretable because it's not defined in the question what P represents.
Oh, would it mean if you put X in the existential part? Would it mean everybody loves somebody? Because
Exactly, yes. No,
okay.
if we make existential X,
Yeah,
then
and
it will be there is someone who loves someone.
oh, okay.
But if you will make this universal quantifier instead of the existential, then you will be right.
Could it be the same meaning if you write for every X there's some Y?
Well, because we know what X and Y are, right? So they are basically the people in the world. So it would not make sense to say X, there exists X, there's loves Y, right? Because so first we place them, we put them in the, so how I interpret it is like, so I will say there is X, there is Y, whom X loves, right? And then I will replace those X and Y with the domain, which is people in the world. Okay, but the final answer will be without X and Y, without those variables. Okay, part number E, there is someone whom Lydia does not love. Part number E will be, there is someone, there exists X, does not love, right? So we will say negation of L, and then, so this person is Lydia. Then we will say here X. Okay. There exists someone who Lydia doesn't love. Okay.
Excuse me. Oh, is it possible to return? I mean, to control Z?
I'm sorry.
Oh, okay. No, never mind. Wasn't Lydia supposed to be instead of Y?
Instead of
Like,
X, you mean? Over here?
yes, is Lydia our Y or X?
Lydia is Y here.
So you put Y first, then X.
Yeah, but it says whom Lydia does not love. It's not like Lydia loves that one.
It's like Lydia is not loved by that someone.
Yeah,
That's what it means, right?
yeah.
So Lydia is our Y, all right?
It basically means that here, so whom Lydia does not love. It's not like that person doesn't love Lydia. It's Lydia doesn't love that person.
Oh, Lydia does not love that person. Oh, okay, okay, okay. So wasn't it supposed to be Y? Like there exists a Y?
Well, here it doesn't really matter because the domain is the same, right? X and Y consist of all the peoples in the world.
Oh, okay, okay,
I can
okay,
put Y here or here.
okay. All right, thanks.
Okay, let's move on to the next one. Question number 13. We have X has sent Y an email message. And this T here, X has telephoned Y, where the domain consists of all students in your class. We have to use the quantifiers to represent them. Okay, let's do part number A. Okay, we have Chow has never sent an email message to Coco. So now how can we represent? So this represent here, X has sent an email message, right, to Y. So here we will say that because Chow has not sent an email message to Coco, so we will represent this using the negation. Negation, we will put Chow and Coco over here. Like this. Okay, this one was a straightforward one. Next is part C. We have Jose has never received an email message from Deborah. Now we will be using the same M function. So negation of M. So we have this person named Deborah. Who has never sent a message to Jose. Okay. Now let's move on to part number E. No one in your class has telephoned Nina, so we will be using the other function here, T. So it says no one, so we will be using for all X. There is no one, right, who has telephoned Nina. Okay. Any questions? Okay, if no questions, let's move forward. We have this question 17. So express each of these using predicates, quantifiers, and logical connectors. part number 2. Well, every user has access to exactly one mailbox, right? So here we are not restricted by those domains, and then those like in this question we are not given the function names, right? And we are not given the variables, so we have to come up with our own. Okay, so let's put it this way. So for all x, right, there exists y, and let's say m represent mailbox. Could be capital. Yeah, remember to make that capital. Okay. X, Y. Then we have to say every user has access to exactly one mailbox. So this statement over here, the problem with this statement is that there exists, it doesn't really guarantee that there is exactly one mailbox. There could be mailbox, but it means that there is at least one mailbox. But we have to say that there is exactly one mailbox. So in order for us to achieve that, we will have to add more statements to it. And then we can say and m
Miss,
yes,
you can use a unique quantifier, right? A uniqueness quantifier for that, can you? Since it
uniqueness.
said, yeah, a quantifier that is only true, only if one is true.
What kind of, which one is that? So there are two kind of quantifiers. This one, the upside down A, it means for all, and this one existential. So
In
there
the
is a third
tutorial,
one you're saying?
I mean, in the lecture, the professor talked about the uniqueness quantifier as well.
Which lecture slide is that?
I think lecture, chapter 1, part 5. Yes, I think, yes. Chapter 1, part 5, the last slide.
So here we have there exist x means that px is true for one and only one x in the universe of disclosure. Is true for one and only one x. Okay. Now here he has also said that this can be expressed this way, right? So we are doing exactly that way. Okay. So this, we, in order to have it like this, we have to, the unique quantifier is not really needed as a restriction that there is a unique x such that, so we can express uniqueness quantifier, or basically this is actually an existential quantifier, but in order to represent one and only one relationship, we have to make it like this, right? So we have the implication, and then there exists an x. Okay, so we will be doing the same thing. Okay, so just hold your questions for a minute. Maybe it will become clear to you. Now we will say there exists a Z. The Z is not equals to Y implies negation of M X Z. Okay, so this one over here closes this one, and then this one closes this bracket, and then we need another one to close this bracket over here. Okay, so now we have a 2. So this is number 1, and then this one is number 2. Over here, this one here, it means that user has mailbox, but we have to say that user has access to only one mailbox, right? So in order to express the level of specificity, we will say that that's an exactly one user, right? So oh sorry, exactly one mailbox, right? So therefore we have to put it in this way, right? So this here, it means exactly one. So we introduce another Z, and then Z is some person as well. And then we're saying that Z is not, so here we have this, there exists what? So it says that Z is not everybody. And then we're saying if Z is not Y, then negation of this X. So this here actually it represents the level of specificity. It basically represents that exactly one.
So the Z not equal to,
this here represents that there is a user who has access to mailbox, and then here it means that, and that is not more than one user. That is exactly one user.
why the negation for the imply? I understand the Z not equal to Y, but why is there negation for the imply?
Basically, we did this because we are saying that it's not, because here we have this X, right?
Yeah.
If we are to read this, so only if we read this part, right? So it will means that X, right? X has access to mailbox Z. We don't want X to have access to mailbox Z. Therefore, we put the negation Z. Okay. So here we are saying that X does not have the access to mailbox Z, and Z is not Y. So therefore it is exactly one person.
So X has access to mailbox Y. Z is not equal to Y, which means that it's only one mailbox
Yeah, it means that if, so here this is implication, right? We're saying if Z is not the same person as Y, and sorry, if Z is not the same person as Y, then X, right? X here, right, does not have access to the mailbox Z. This here combined means that we're talking about exactly one person. Okay, let's take another example. Part C. So here we will say all users on the campus network, all user, they exist for all users, all users on the computer network can access all websites whose URL has a.edu extension. Let's maybe represent this X using user. So let's put U here. So for all users and for all sites. So sites is S. And then we can represent the extension with E. S, then dot E D U edu, then that access US. Okay. So here, this one here, over here, this part over here, this is part 1. This is part number 2. So here, part number 1, it basically means that website S has extension .edu. Okay, and then this part number 2 here, it means that user U, which is represented by U, can access website S. So we are saying if S ends in extension edu, then user U has access to that website. Okay, and then we are generalizing it for all the users and the websites. Okay, so all users can access all websites whose URL has .edu extension.
Is it because it has the keyword whose? Is that why you used an implication?
I'm sorry, for what keyword?
Is it because it has the keyword whose, like WHOSE? Is that why you used an implication?
Yeah, well, the reason why I used is it because it sort of declared an dependency on one another, right? So something has to be true, right? Then something else can happen. So the website got to have .edu extension, then only the students will be able to access.
Yeah, yeah, makes sense.
Make sense?
Yep.
Okay. Okay, let's take another question. The one. So we have to represent the statement that every positive number is the sum of the squares of 4 integers, right? How do we represent this thing? Okay. So we have to come up with the variables that represents the 4 integers. So let's say that those are a, there exists an a, there exists a b, there exists a c, and there exists a d. Okay, so we have these 4 numbers, and then we are saying that it's is the sum of the squares of 4 numbers. So there is a positive integer, so we have to get that positive integer, which is represented by x. Right, then we represent that every number, that every positive integer, so it means that it's true for all of them. Okay, so we have these 4 numbers, and then the fifth is the sum of those numbers, and then we are saying that x is positive. So how do we represent x as positive? X is greater than 0. So we know that this is positive. So if x is positive, then what happens is x is the equal as x is equals to the sum of their squares, a square plus b square plus c square plus d square. Right?
Yeah, right. Yeah.
And this one was a little easier. Put them on the side. Okay. Now we have this question number 25. Here it says translate each of these nested quantification into an English statement that expresses a mathematical fact. Okay, basically we have to translate them into English ones. Okay, so let's take part number A. So part number A, we will say that there is a, so we know that x, y equals to y. This is a multiplicative identity for the real numbers. Okay. Part number C, Likewise, we'll say there exists real number x and y such that x square exceeds y, but x is less than y. Okay, so we have this, there exists real number x, and then there is a y for which the square of x is greater than y and x is less than y. You can replace this but with and as well, or similar terms. Questions? Okay, let's move forward. Question number 29. Here we have to determine the truth values if the domain of all variable consists of all integers. Okay, well, here we have to say that, let's do A. All right. So we have that n, and then there exists an m. So we are saying that the square of any number, all the numbers, is always less than m. So there, for all the numbers n, their square is less than some number m, right? So for example, we have 4, the square of 2, right? So if we take n equals to 2 and we take m equals to 5, then this statement is true, right? So because 4 is less than 5, right? And then we could also generalize it for all the integers, right? So there is a number always who is greater than the square of the other number. So we will say that this statement is a true statement. Moving to part C. We are saying here that n plus m equals to 0. Well, this statement here is also true because n, I take any n, but I take m, right? And I add it to n and it will equal to 0. Well, maybe if we take n equals to 2 and equals to 2, and then I take m equals to minus 2, then it's equals to 2, right? So I can take always m the same but negative of n to make it equal to 0. Part E. So we have n squared plus m squared equals to 5. And then here we have there exists. It's not true for everyone. It's true for some of them. This is also true because if I take, let's say, n equals to 2 and I take m equals to 1, right? And I put these values inside. So 4 plus 1 equals to 5, which is true. And then therefore, like there exists. Okay.
So that doesn't mean that any one condition is true, then the whole thing will become true.
Sorry, your voice is not clear.
For this question, if just one condition is true, then the whole statement becomes true for this type of question.
I cannot really understand. It's not clear, the voices. Probably you can text me. I can look into the text.
Miss, so that for every n, you have to choose one number and
Well,
Do you have to choose a number?
in order to prove this, right? So we have to check the quantifiers, the domain. Is it true for everything, or they're asking like it's true for something, right? But because we proved like it's true for something, right? And then they ask for something, so we know that this statement is true. But if we change the quantifiers, let's say if I make this existential, I can make this a for all quantifier, right? So then this one here will be false.
Why is it going to be false?
I'm sorry?
Why is it going to be false?
Why is it going to be false? Well, because this statement can only hold for few of them, right? They cannot hold for all of them.
Oh, okay. It can't hold for all the numbers.
Sorry again.
It can't hold for all the numbers.
Yeah, it doesn't hold for all
Oh,
numbers, right? So
okay.
because let's
I
say
get
if
it now.
I the counter example, so if I change this n existential to for all, right? And then I come up with n equals to, let's say, 10, right? Or maybe anything greater than 2. This statement will become false because then it won't equal to 5. Okay, so this was a relatively easy example, not that hard. Let's move to the last question of exercise 1.5. So we have to rewrite these statements so that the negation appears only within predicates. That is, that no negation is outside a quantifier or an expression involved with logical connectives. Okay, basically here what they're asking is like we have to rewrite these statements so in a way that the negations appear only within the predicates. Okay, so here we have these negations, right? They are outside the quantifiers, like they're beside the quantifier, so we have to make them outside the predicate only. Okay, let's take this part number A here, part A. So this part A, we can express it like there exists X, right? Well, this negation, it got multiplied by all of them, right? So this for all X, right? When with negation, it becomes there exists X. This, then this negation, and then this for all Y becomes there exists Y. Right? And then we have this negation that gets multiplied with this predicate X, Y. X and Y. Cool.
Yep.
Okay. Pretty easy there. Let's move to part number, let's do the hardest one, maybe E. Same thing. So we will be saying that there exist X, right? Because of this negation. Remove this inside. For all Y. For all Y, there exists Z. Right? So basically negation makes them opposite, the quantifiers, right? And then we just say negation of P X Y Z, right? This and when it becomes not and, it becomes or, right? And then this becomes for all z, there exist a y negation of p x y z. Okay, so this is relatively easier compared to the other questions. Okay, any questions here?
No, it makes sense.
Okay. Okay, so this completes our exercise 1.5. Hopefully it covers most of the ideas. So now let's move on to exercise 1.6. Exercise 1.6 is mostly based on the rules of inferences, right? So like modus ponens, modus tollens, addition, subtraction, and these kind of rules. Okay. So I believe like you guys have already went through the slides and have enough understanding for this.
Yeah.
So let's do the part number 1 here. We're asked like, what can we conclude? Is this even true if the premises are true? Well, this rule that applies based on the rule that we will be applying. So the rule that we will be applying is modus ponens. And then we say that this is valid because if the premises are true, and then based on that rule modus ponens, we know that the conclusion must be true as well. Because the hypotheses are true. Let's move to the next one. That was pretty simple. So we have to basically here tell which rule of inference can we apply on these ones. Okay. So here we have what type Alice is, part number A. Part number A. So Alice is a mathematical major. Therefore, Alice is either a mathematical major or a computer science major. Well, we have to think about what rules we can apply on this statement. Let me open up the slides on the side. Okay, so here, if you will see that this part number A here, we can apply the rule of addition here. Because it says here that Alice is a mathematical major, so we only have one hypothesis. So we are concluding that Alice is either a mathematical major or a computer science major. So this statement over here, P or Q, will be the addition rule. Part number C says if it is raining, then the pool will be closed. Well, in order for us to know like what kind of rule we can apply, we can basically check with what form a rule of inference form can we apply on this. And we can apply the rule of modus ponens here, because we are saying that if statement, so if it is rainy, so it has to be some rule which contains the implication sign. Okay, so we have this: if it is rainy, then the pool will be closed. So let's, if it is raining, be represented by P, the pool will be closed, it's represented by Q. And then we're saying it is rainy, we are asserting that it is raining, so this P here, therefore the pool is closed, hence this Q. Okay, so modus ponens. So P, so for the E part, what we're saying is, if I go swimming, then I will stay home stay in the sun too long. If I stay in the sun too long, then I will sunburn. Therefore, if I go swimming, then I will sunburn. This is exactly the format of this rule of inference. So we will say that this is hypothetical solution. Okay. Any questions? No questions. Let's move forward. So we have a use rule of inference to show that the hypothesis, if Randy works hard, then he is a dull boy, and if Randy is dull boy, imply the conclusion. Okay, so how can we say? So we can say let W, let me increase the font size. If let W be Randy works hard, we will just assign those variables to those statements. Then we say let D be Randy is a dull boy. Lastly, we will assume let J be Randy get the job. So we have those hypotheses. The hypotheses are W, right? So we will just this list will be, we have W, right? Because we have said Randy works hard, and then we have if Randy works hard, then say he's a dull boy. So we say W implies D, and then we find here D implies, we have this negation sign here, negation of J. Okay. So this is the three implications that we can find from these statements. Okay. And now we have to use the modus ponens rule and the first two hypotheses. So let's use modus ponens. Maybe if I can open up the paint, it will be easier for you guys to see. Okay, so here Let's put the question on the side. Okay. So now what we will be using is we will be using the modus ponens rule on the first two hypotheses. So the first hypothesis is W and W implies D, right? So using modus ponens here, we know that if this is the case, then we get Q as the conclusion. So Q in this is this our D, right? So we get the D, right? So therefore, this is our another one of the assumption towards the final solution. So we have 1, 2, 3 assumptions, and then we find the fourth one. Okay. Now, what we said is Randy will not get the job. So here we have to say, and if Randy is a dull boy, then he will not get the job. We say that Randy is a dull boy. We already got this, right? So Randy is a dull boy. Now, Randy, so this is the fourth here. Now we have this third modus ponens rule of inference. This third hypothesis over here, D negation of J, right? So we use these ones here. So we find the fourth hypothesis, and then we use this fourth hypothesis and the third hypothesis over here, right? So number 4 and third hypothesis over here. So we apply the modus ponens rule again, and then we get negation of J, which basically means that J represents Randy will get the job, so negation of J will represent Randy will not get the job, right? And this is what we have to find. Randy will not get the job. Questions? No questions? Okay, if no questions, let's move forward. So for each of these collections of premises, what relevant conclusion can be drawn? Explain the rule of inference used to obtain each one. Okay, so we have to basically take these ones. Let's take here. Okay, so let's do the part number A here. Part number A. So we have this, if I take the day off, it either rains or snow, right? So let's say day, we represent this day. If I take day off, then what happens is either rains, right, or snow. Okay, and then we're saying I took Tuesday off, so we took a day off, which we make sure that this is actually satisfied. Or I took Thursday off, so it was a Tuesday. Tuesday is off, or we take Thursday off. Thursday off, right? Which are basically days. It was sunny on Tuesday. I did not. It was sunny on Tuesday, and then we say that it is sunny on Tuesday. It did not snow on Thursday. Did not snow on Thursday. So basically, from this, what we can conclude is that so what we can conclude from this one here is that I did not here for part A we're doing. So it will be I did not take Tuesday off because on Tuesday it was sunny, right? This is one, and the other one conclusion that we can draw from here is I took Thursday off because on Thursday it did not snow, right? But it could have possibly rained on Thursday, right? So this is another possible conclusion.
Yes, makes sense.
And then the other one could be it rained on Thursday. Moving on. Part C. I am either clever or lucky. I am not lucky. If I am lucky, then I will win the lottery. We have to say that I am either clever or lucky, but here it's another hypothesis. I'm not lucky, so I am clever is one of the possible conclusion, right? If we apply the modus ponens rule to these first two hypotheses, right? So I am clever will be one of the conclusion and the only one. Moving on to part number E. What is good for corporation is good for the United States. What is good for the United States is good for you. What is good for corporation is for you to buy lots of stuff. One is that you buy lots of stuff that you buy lots of stuff is good for the US and for you. Okay, because here it says what is good for the United States is good for you, and then it says that good for the corporation is to buy a lot of stuff. So if I buy a lot of stuff, then this is good for the United States and it is good for me. Well, this don't relate this to the actual truth, so this is just a statement. Okay, so this is one of the valid conclusion for this from this here. Any questions? Okay, so no questions. Let's move to the part number 13. So in these ones, we have to basically explain that the rule of inferences. It's a little bigger question. So let's take the part number A. So here, okay. So here, part number A, we're doing part number A. So Doug, a student in this class, knows how to write program in Java. Everyone who knows how to write program in Java can get a high-paying job. Therefore, someone in this class can get a high-paying job. Okay, so here, because we know that, so let's represent A with this statement that Doug is a student in this class who knows how to write program in Java. Okay, so here we will be having those premises. So there is in class there is a student named Doug, right? And then Doug knows Java, right? And then we know that everyone, so let's say X be the student who knows Java, everyone who knows Java, then he can get a highly paying, that person can get a highly paying job. Okay, so everyone over here, everyone who knows how to write program in Java can get a highly paying job. Okay, so this is, so these ones are our the premises, right? And then we have to deduce some other premises. So because we know that here Doug, right? So we will use this fact that Doug, as he's a student in this class, and he knows how to write. So we will just replace this with X with Doug. Okay. So here we have J of Doug. Right. So we just replace this X with Doug. Okay. Okay. Now we know that these ones are true. Now we have to find out more hypotheses by applying the rules of inferences. So if we apply the rule of inferences, let's say, so let's number them. So let's say this one is number 2, this one is number 3, this one is number 4, 2, 3, 4, and this one is number 1. So if we use modus ponens on number 2 and 4, so if we have 2 and we have number 4, then what we get is H of Doug. So H of Doug. So we found another hypothesis, which we're gonna call it number 5. Okay, so we have to say someone in this class can get a highly paying job. Okay, so we have to find this conclusion. So now we have to use the here rule conjunction, right? So we have this P, Q, and then we can just do and between those according to this conjunction. So we have this number 5 here, and then we add a number 1. Then we apply the rule of conjunction here. So 5 and 1. So we apply, we have this here, and then we have this here. So we get C, Doug, and H, Doug. Now we have this another one, we call this number 6. Okay, we have to, what we are trying to do is basically we're trying to find this, that someone in this class can get a highly paying job. Okay, so now we have this, and then we will be using another rule of inference. So we will be calling that rule of inference. Basically we will be using the quantifiers, right? So we know that Doug is in this class, right? So therefore we can say there is a student in this class because Doug is a student in this class, right? And then he is a student of this class, so C of X, right? And he can get a highly paid job. So based on our assumptions, we find the conclusion that there exists someone who is a student of who is in this class. He can find a highly paid job. Questions? Okay. No more questions. Let's move forward. So we have this, what is wrong with this argument? Let H, X be, X is happy. Given the premises, there exists someone that is happy. We can include that H of Lola. Therefore, Lola is happy. So we have to find what's wrong with this argument, right? So here, so here we have to have been given the hypothesis that H of X, right, which means X is happy. So we know that we know that someone is happy, right? But because of this, there exists, right? But we cannot conclude that Lola is in the domain of X, meaning Lola may not be in X. Okay, so we were basing our conclusion on the wrong hypothesis. Okay, because we don't know the domain of X. Any questions? Okay, let's move forward. No questions. So we have this question over here, question number 23. So we have to identify the error or errors in this argument that supposedly show that if we have this is true, then this is true. So we are starting with a premise and then we are concluding something, right? But we have to find out if there is any problem with this. Okay, so we have this premises given, so there exists px or there exists q of x. Okay, let's and then they are applying simplification to get this, right? So on here, so if so they are applying simplification rule on this premise, but they cannot apply this simplification rule because they need to be and there should be a conjunction between them, but here there's a disjunction. Okay, so this is one of the errors. Now supposedly the answer is this, and then we are applying existential instantiation from 2. So what is existential? It's not mentioned here. So basically here existential instantiation is, so when they pick up C from one of the domains of X, so they have a C in X, so they just took out C, so which is good. So they're applying simplification from 1 to get this. Again, this is not correct because they cannot apply simplification on or, they need to be and, right? Now on line number here 5, here they are picking C again using the existential instantiation, so which is okay, and then they're using conjunction rule. So conjunction rule here is when you have P and Q, then you get P. So here they had 3 and then the 5, so they use the conjunction rule to get this, so which is good as well. And then they are using existential generalization to get up to this, so this one is good. So again, so we find that there is one problem over here, that when they uses the simplification to get this hypothesis, and then the other one is when they use simplification to get this as well. Okay, questions? Okay, if no more questions, let's move on to this one. Question number 39. It says use resolution to show the hypothesis. It is not raining, or she has her umbrella. Does not have her umbrella, or she does not get wet, and it is raining, or it does not get wet. Imply that she does She does not get wet. Here we will represent, so let P be it is raining. Let Q be it has her umbrella. Let R be if it gets wet. So we have these assumptions here, and now okay, so let's take this to there. Okay, so we have these assumptions over here, and then we're gonna put them in this part. So we have this negation of P, right? If it is not raining over, with her umbrella. So this one, or Q, it is not raining, or she has her umbrella. So this is our number one. Number two is gonna be that negation of Q or negation of R. Negation of R. So this is our number two. Then we have another, so P or negation of R. So this is our third one, right? So it is not raining. So this is the first one. She has an umbrella, second, and it is not raining. So this is the third one. So we are supposed to find out if this is true, if these premises are true, right? So we assume that these premises are true. Okay. So now we apply the rule of resolution here. So resolution rule says the negation of P or R, P or Q, and we can imply Q or R here. Okay. So now we apply the rule of resolution on these two and three. So we apply rule of resolution on them, and then we get another hypothesis, negation of Q. So we have this negation of Q or negation of R. We have this P or negation of R. Negation of R. So we apply the rule of resolution like here to get so this one is where we will be applying the rule of resolution, not this one, because we cannot apply rule of resolution over here. So on 1 and 2, let's apply the rule of resolution. So negation of P or Q, negation of Q or negation of R. We apply the rule of resolution because here Q and we have not Q, so we can apply. So they will basically cancel out, and then we have negation of P or negation of R. So this is going to be our fourth one, right? So now we can now apply a rule of resolution because we have negation, we have this P here, and then we have negation of P. So now let's apply on 3 and 4. So P or negation of R, and then we have negation of P or negation of R. So applying the rule of resolution, so this is going to cancel out with this one. So we have negation of R or negation of R. So we have these negation of R. So we know that whenever we have something with an or, we already stated in the previous one that the previous tutorial that whenever we have this negation of a P or P, this is logically equivalent to just the P itself. In this case, the P will be negation of R. So our hypothesis was R represent she gets wet, but we were saying that she does not get wet, which we have also proved here. She didn't get wet. Okay, any questions? Any questions, guys?
No, I personally don't have a question.
Okay. So so in this tutorial we covered exercise 1.5 and 1.6. So again, like I mentioned before, so if we didn't cover exercise 1.4, it's covered in the other tutorial. If someone has a specific question for the exercise 1.4, they can just email me, but just email me like at least 2 hours advance, so I can keep that in mind. Okay, so if no one has any questions, then we could probably end the tutorial here. Okay.
Okay, thank you, Professor. Thank you.
All right.
Yeah, thanks, man.
All right. Thank you, guys. We'll see you in the next tutorial on Thursday, 5:30 p.m. Okay.
Okay, thank you.
All right. Have a good day, guys.
Bye.
Bye.